Okay, so imagine that we want to build a large cylindrical fish tank. And now if you think of having fish in the cylindrical tank, you of course expect to have a bottom but no top. You want to have some air for the fish. So assume that we want our cylindrical water tank to be able to contain up to 150 cubic meters of water. And imagine that we are going to build this tank using two different types of material. We are going to use plastic for the base of the tank. Imagine like some kind of thick plastic. And for the body of the tank, we're going to use glass. Thick glass so that we can see the fish in the water tank. Now we expect that the cost of glass and plastic will be different, so assume that the cost of plastic is $5 per meter squared, and the cost of glass you would expect to be much higher. It says $17 per meter squared. So now we want to build this tank. So we have a bottom plastic with a glass body, of course no top. So we want to build this tank. And if you think about this, the natural objective is to build this tank in the cheapest possible way, still having a volume capacity of up to 150 cubic meters. So of course, there are two measurements that we have to figure out. There is the radius of the tank, and of course the height of the tank. So let's figure out now a cost function. Now, how do we go from having, for the glass and the plastic, a cost per meter squared to a total cost function for the tank? Well, think about this. We have, in each case, for the glass or the plastic, we have a cost per meter squared. So how do you then go from a cost per meter squared to an absolute cost? Well, that of course is how much of any given material you're using. So if you think about this, if you do cost per meter squared times meter squared, the meter squared will cancel, and you're left of course with an absolute cost. So meter squared of course is the area. So this measures how much of either material we're using for each part of our tank, the bottom and the body of the tank. So let's call the absolute cost function C. So C will be equal to, well, first, what is the area of the base? Well, it's circle of radius r, so it's pi r squared. So we have pi r squared meter squared times $5 per meter squared. This will of course leave us with dollars, right? We're doing the area of the base times the cost per meter squared. So this returns the total cost of the base of our tank. What about the body? If you recall thinking of the body as a rectangle, by cutting one side open and flattening it out, we have a rectangle of height h and length being the circumference 2 pi r. So the area of the glass used is 2 pi r h. That is the total area of glass that we're going to need, times of course the cost per meter squared will give us the total cost of the glass, times 17. So now we have the cost function. The only problem again is that we now have a function of not one but two variables, of r and of h, so we can go back to the restriction to solve for h in terms of r, right? If I write it here, the volume is 150. Let me drop the units. And the volume, of course, of the tank is area of the base times the height. So it's pi r squared times h, divided by pi r squared, so h is 150 over pi r squared. We can now make the substitution. I can put up the 5 here, so I have 5 pi r squared plus. I can pair the 2 and the 17, so 2 times 17, 34, so plus 34 pi r times h, and h is 150 over pi r squared. We can simplify a little bit here, so 5 pi r squared plus 34. Now the pi over pi will cancel. The r over r squared and r will cancel, so we'll be left with 150 over r. And I will not multiply 34 and 150. I will leave it as 34 times 150 for now. And again, thinking of differentiating to obtain a minimum of our cost, we want to avoid a quotient if possible, so if we just bring the 1 over r as an r to the negative 1, this will reduce to the power rule, which is simpler. So we now have a proper objective function, which we want to minimize. The total cost of constructing this water tank. The cost will be a function of r, which is 5 pi r squared, plus 34 times 150, times r to the negative 1. So r must be clearly positive, and no matter how large we take r to be, we can always take h to be 150 over pi r squared, and the volume will still be 150. So there is no upper bound for how large r can be. So all we have is that r is some positive number. So as we want to minimize a function of one variable, and we do not have a closed and bounded interval for the independent variable, we need the second derivative. So let's differentiate the cost function twice. And again, this function is in dollars, but we omit the units for now, and at the very end we can include them back in our conclusion. So let's differentiate. So C prime. 5 pi is a constant multiple, so it will stay there. Derivative of r squared by the power rule to r, plus 30 times 150 again is a constant multiple, so 34, sorry, times 150. Power rule on r to the negative 1, negative r to the negative 2. Second derivative, five pi times 2 is a constant multiple, we can write as 10 pi, times the derivative of r, which is 1, plus 34 times 150, times the derivative of negative r to the negative 2, power rule again, bring this down, positive 2 now, times r to the negative 3. And there's something interesting that we can notice. Since r is positive, the second derivative is a sum of two positive terms, so it is always positive. But if the second derivative of the cost function is always positive, then the graph of the cost function is always concave up. Of course, if the radius is positive. And the fact that the graph of our cost function is always concave up bodes well to have an absolute minimum. Now if there is a minimum, it will have to occur at a critical point, so a point where the derivative is 0. So we want to solve for this. So the derivative will be 0 if and only if this will be equal to 0. So 5 pi times 2r plus 34 times 150 times negative r to the negative 2 is equal to 0. And now we can solve for r. Now the first thing is, both are multiples of 2, so we can cancel a 2 across, but both are also multiples of 5. So we can divide across by 10 to make things quite nicer. So if you divide across by 10, 5 times 2 cancels, and 150 over 10 of course is 15. So we're left with something a little simpler. Pi r. Now 34 times 15, well, that's 340, plus half of that gives you 510. Negative, so negative 510. And I'll write the r to the negative 2 as a over r squared. This has to be 0. Let me send this onto the other side. So pi r must equal 510 over r squared. I can multiply by r squared, divide by pi, which gives me that the radius cubed, right, r times r squared is r cubed, equals 510 over pi. I can solve for r by taking the cube root on both sides. So the radius must be equal to the cube root of 510 over pi, which is, if you want an approximation, approximately 5.455 meters. So now we have our critical point, and again we can sketch a very rough graph of our cost function, since we know that it has a unique critical point, about 5.45, and the curve is always concave up. So the critical point we found has to be an absolute minimum. Again, we will not find the exact value of the cost. You could, if you plug this back into the cost function, you will find the exact cost of building the tank, and that of course will be the smallest possible cost. But again, at this point, at this value of r, the derivative was 0, so the curve here is flat. The graph is always concave up, so it can only look one way, more or less as a parabola. So our unique critical point has to be the absolute minimum. Now we're left with finding the height of our tank, right? We wanted to construct a tank that could contain up to 150 cubic meters of water, and that was as cheap as possible. So we found the radius, about 5.45 meters. What about the height? Well, the height, if we go back, was 150 over pi r squared. So we can plug back in. The height was 150 over pi times the radius squared, but we now have the value of the radius that leads to the smallest cost of construction, so we can replace. This is 150 over pi times this squared. This is a power of 1 over 3, times 2 is 2 over 3, so we have 510 over pi to the power of 2/3. And if you want an approximation, use your calculator, and you will find that this is approximately 1.604 meters. And these are the measurements that will lead to a tank that can contain up to 150 cubic meters of water, and that is as cheap as possible. And again, I will leave this up to you. If you wanted the exact cost of building the cheapest possible tank, take the exact value of r and plug it back into the cost function, and you will obtain the cheapest possible construction cost of the desired tank. And that's it.